I'm thankful to Professor Mukul Shukla sir to pave the stage for my talk. He already introduced you to the all the aspects of additive manufacturing, the limitations, the uses of AI, and the functionality of the parts which can be used in starting from drone to the defense or to the aerospace parts. So I will start my talk with there only, and we will focus more on the modeling part, which AM PravaH can assist you in big time. So this is going to be my talk. The first I would like to introduce the motivation around modeling and simulation of my work. Then I will quickly introduce you to the LPBF, which is laser powder bed fusion. And the most important part of this talk is how you all can utilize AM PravaH tool to perform the modeling and simulation of LPBF or other additive manufacturing like VEM and other DEDs. And I will, at the end, I will showcase you the case studies which we have done with the help of AM PravaH, and we recently presented it in one prestigious conference at IIT Madras. So the motivation, as sir already established the stage, but still I want to ask the audience why we need modeling and simulation in additive or in any other fields. So as in AKGC, where I am sitting right now, we have a metal 3D printer of few crores, so we can directly print the parts, and one can say why we need modeling, why we need simulation. So to answer that, I have added one slide or one image from LinkedIn post. That post is made by NCAME, that is in Auburn University, Alabama, and they have showcased that how these constant amplitude loading is not much relevant when we're talking about some in-service parts of geometries like this, and we have variable amplitude loading. So the point here is that geometric dependent thermal history. What I mean to say is, if your part, like in aerospace or defense or automotive, wherever you are applying additive manufacturing, in particular metal one, you cannot have simple constant amplitude loading, and you have to acknowledge different amplitudes, different geometric constraints on the actual functional part. So just by printing simple samples, standard samples, you cannot predict the life, and it is a cyclic loading that could be very detrimental. So actually you have to furnish that geometry or that process in modeling and simulation. You have to represent it mathematically. You have to solve these equations. You have to solve or imitate that actual scenario in modeling firsthand. You cannot directly risk the part to fail during the service. So that is the idea. And just to introduce a bit of LPBF, additive manufacturing as of standard definition, process of joining materials to make parts from 3D model data. We're going to start with the 3D model data, usually layer upon layer, as opposed to traditional manufacturing, which is known as conventional. So as per standards, we are going to discuss more on the powder bed fusion, but we have wet photopolymerization, material jetting, binder jetting, material extrusion, sheet lamination, direct or DED. So this talk is more focused on powder bed fusion, and we have different metallic powders. We can use steels, titanium alloys, nickel alloys, aluminum alloys as per the desired applications. These are the few application areas like automotive, aerospace, medical sector, as Mukul sir has already told you, the surgical implants, the energy sector, the industry tooling sector. And these are the basic algorithm. We start with the pre-processing, we fabricate the part, and we do the post-processing. So what are the benefits that Mukul sir already covered, but I want to talk about the limitations. And the first one is multi-scale multi-physics that I want to talk about. So in metal additive manufacturing, or you can say in laser powder bed fusion, there is a multi-scale multi-physics involved during the process. I'm going to elaborate it further, but you have to acknowledge that there are multiple physics simultaneously happening at a very small time scale, and you have to capture that physics to actually predict the final properties, final build qualities. So modeling and simulation is essential in that part, and a software or a tool like AM PravaH, a module like AM PravaH can help you with that. So laser powder bed fusion, as many of you maybe already know, but it starts with laying up a powder bed, and the laser will selectively fuse the powder wherever we want the material to be solidified. And layer by layer, that 3D part can be generated. So layer of powder is built on the platform, laser fuses the layer, new layer is spread with the help of recoater, and further layer are fused, and the process is repeated till we get the final 3D part. There are various original equipment manufacturers, Nikon SLM, 3D Systems, EOS, Germany, Farsoon, Intec, Amaze. There are so many OEMs available for producing LPBF systems, but we again have to go for the just a quick overview of the current trends on the metal AM. The sales are increasing year by year, as the sector is evolving into many domains like defense, aerospace, tooling, or energy. These are some complex parts. Sir already showcased you some very intricate objects. So these are the case studies. And now I have established, or Sir has already established, the beauty of the AM. Now we have to talk about the villains here. And as you can see, the parts, there are some failures. You can see some delaminations, some lack of fusions, and a chunk of powder you can see in this slide. So I'm going to talk about the technical challenges or the multi-physics challenges in LPBF. And these are, you can divide them in few categories. The first and the major, villain of the metal additive manufacturing is this lack of fusion. As the name suggests, the fusion is lacking. So that means the fusion is not proper. Why it is so? It can be of any reason, improper process parameters, improper powder material, improper power supply. The another one is balling, which is, these kind of balls are in surface due to multi-physics of surface tension, improper scan speeds. We have keyholing, and we have shrinkage. So let's elaborate it further with some images. Yeah. So one experimental study from 2019, you can see a different melt pool shape here in every micrograph A, B, C, D, E. Somewhere we have a keyhole like melt pool, whereas we can have a stable melt pool, which is desirable in many of the cases. So how these different melt pool structures are coming into play because of these parameters, which can be laser power, scan speed, layer thickness, edge spacing, and as well as some auxiliary parameters like spot size, preheat temperature, scan strategies, build orientation. Apart from that, we have material constraint, which kind of powder morphology you are using. In the preliminary classes, it is always advised that the powder particle should be spherical. Non-spherical particles can be detrimental for the powder, powder bed fusion. And there are various research, that are focused on that type of morphology of non-spherical powder particles. So I'm trying to establish that these all parameters can affect these type of melt pool structures. And once you produce that part, there is no going back. So first hand, you have to establish how the melt pool is going to be produced. You have to predict it, you have to simulate it, you have to model your process. This is the big picture of multiphysics, as I'm talking in the previous slides. The multiphysics natures include the laser powder interaction. Laser is going to interact with the powder. We have recoil pressure that is going to affect the laser trajectory. We have phase transformation, that means solid to liquid, liquid to solids, and some evaporation as well. We have powder morphology, as I have talked about. We have Maragoni convection, which is very important. This is nothing but a derived property of surface tension. How surface tension is going to affect the flow of the metal within the melt. We have heat conduction to the substrate. The substrate is going to conduct some heat. We have convection and radiation heat losses. So all these multiphysics, you cannot predict it. You cannot analyze it in the physical setup of LPBF of any other machine. Definitely you have to model it, you have to simulate it to analyze these effects, how these parameters is going to affect these multiphysics natures. This is the motivation of modeling and simulation. When we have started, Professor Mukul Shukla always inspired me to do the modeling and simulation for the betterment of the our previous research works, because sir has already supervised 2-3 PhDs on rigorous experimental works on the metal additive manufacturing, starting from titanium or molybdenum alloys, from miraging steels to aluminium alloys. But we want to model, or we want to simulate that process in the context of detecting the defects, detecting the processes. This is the motivation. We can have two ways. We can go for the numerical or mathematical or computational modeling. And as sir rightly said, the buzz of AI and ML, so we can go for data-driven modeling as well. So numerical modeling, we can have different domains. We can design for additive manufacturing. We can model the process of additive manufacturing. We can model the microstructures. We can model the cross treatment like hip process, etc. This is the important slide, that if we have decided that we have to model or we have to simulate the process, on which scale we are going to model it. We can model it on a part scale, on a big part scale. We can model it on a melt pool scale, on few microns, or we can simulate the process on the particle scale, which in case of LPBF is powder. The beauty of advanced modeling tools like AM PravaH, Flow 3D, or COMSOL, you can see that they can integrate these scales as well. For example, we can simulate the powder bed with the particle scale model. We can simulate the melt pool, and we can also simulate the whole part for residual stresses or distortion. So a good module or a good tool at your disposal must have all these characteristics, that it can entertain on the particle scale, it can entertain on the melt pool scale, or at the parts, because the whole picture needs to be cleared, as you have as you want a big understanding of the process dynamics. A brief part of data driven or AI modeling, as sir rightly said, that we need a high fidelity data first. On if you want to train any model, if you want to train any machine learning or deep learning, whether it is convolutional neural network, whether it is neural network, you have to start with a data set. That data set need to be high fidelity data, that need to be a bigger data set, not a very small one. So this is the major challenge. We can you can work on that data, and you can develop some fine data driven models. So now we are going to jump for the AM PravaH, how AM PravaH is going to help you. Before that, we have already, we have in the market, we have different numerical and data-driven modeling tools. You can have ANSYS, SimUFACT, NX Additive, Flow 3D, COMSOL. For data-driven modeling, you can use MATLAB, you can use Google Colab, Jupyter, or Spider Notebook. But I am again telling you, when we collaborated with AM PravaH, they have these two modules integrated within the AM PravaH. You can numerically, computationally modulate or model your process, and you can apply the data-driven or AI modeling as well. So a Indian-based product, AM PravaH, can can be utilized for numerical as well as for data-driven modeling. So now the main crux of the talk, how AM PravaH can help for the modeling and simulation of LPBF, whether it is multi-track, whether it is multi-track or multi-layer as well. So this is I took a snapshot from their module, just to showcase you the UI of the this beautiful tool called AM PravaH. So they have, as I am previously telling you, that you have to choose the scale of the modeling. So you can scale on the macro scale, the part scale. You can choose the microstructure modeling. You can use the module of dedicated artificial intelligence tool inbuilt in the AM PravaH. So this is the UI, and you can have a access to the wonderful videos that they have on their YouTube channels or their websites to get familiar with the UI. So now I'm talking about a one of the case studies that we have done for simulating the multi-track laser powder bed fusion for Inconel 718. Apart from this study, we have previously published a few research around modeling of LPBF only with the same material system, but with different tools, with different commercial available tools in the domain of additive manufacturing. What we are, when we collaborated with AM PravaH, what we find that we can have, a more comfortable UI. We can have a more, streamlined process for modeling, and directly you can select the material. You can, select your process parameters. You have to calibrate your process parameters, your physical constants, and you can predict the melt pool geometry. You can predict the thermal cycles, which are going to be important to understand the whole process. So this is a case study. So the numerical model consists of, the first part is DEM simulation. This is discrete element method, which is used to model, or which is used to simulate the powder bed. As in the LPBF, we are starting with the powder bed. The first point should be simulating the powder bed. In earlier simulation studies, generally when they are not able to simulate the actual powder bed, they start with a solid plate, and they try to analyze what difference in the actual scenario. And it is obvious that if we are starting on a solid plate, the results would not be same as we are going to start on a powder bed. So this DEM simulation is really important for LPBF, and AM PravaH has a dedicated module, or a similar tab to simulate the powder particles along with their diameters, their properties, their densities, their material properties, etc. Then you have to simulate or model your heat source, which is laser in this case. So modeling laser with the content of heat distribution, how heat is going to distribute. As you have seen in few research papers, some is going to use a cylindrical profile, some is going to use a double ellipsoidal profile. So you can tune, or you can play with these parameters of heat source, which kind of heat source is more comparable to the actual scenario. When the actual laser is going on, which kind of heat patterns or heat distribution is going on. Then the most important part is multi-physics models. You have to integrate evaporation, you have to integrate the recoil pressure, you have to integrate the conduction, convection, radiation coefficients, you have to integrate the Marconi convection, the surface tension, the Fresnel coefficient, and so on. Those who are not from the dedicated metal additive manufacturing areas might feel it a bit difficult to understand all these terms, but you can start with the, if you are interested in this domain, you can start with some basic research paper, and you get acquaintance with these terms which I'm talking about. So the very important part is this multi-physics models enabled in the AM PravaH module. Then obviously for any modeling, you should have certain boundary condition, which boundary condition you are going to use. In our study, we have started the validation with a single track model. When I say single track, we are just producing a single track of laser fusing the powder particles. Then we predict for the multi-track model, we analyze their thermal history, we validate that thermal history from some existing experimental study or our own experimental study. So this is a basic workflow of a simulation study. You have to model your process first. You have to validate the parameters. Why it is so? Because you have to calibrate that process parameters. How you are calibrating? Because you have to attain the actual scenarios that are happening in the machine when the laser actually works on the powder. You have to predict whatever you want, and you have to analyze these results. How you can utilize these results to to select or to optimize your process. That should be your idea. So these are the beautiful images from AM PravaH tool. This is the powder bed distribution when the powder is distributed on the substrate, and you can see the different size of powders, because in actual scenario, whenever you order some powder from a vendor, they will give you a powder sheet, and they will give you that details that the powder size is like 15 to 45 microns. So the powder particle size is distributed over this range, and you can actually model that powder distribution in AM PravaH, sliding from powder diameter, powder density, powder profile as well. Then we go for the single track model, and we start the laser from here, and we fuse the laser, the powder particle from laser, and we can extract the cross-sectional view of melt pool, and we compare this melt pool with the actual reported results of experimental micrographs. So the idea is, there is a study, they have used certain parameters, certain laser power, certain scan speed. That parameters along with calibration you can utilize to simulate this actual melt with the use of a software called AM PravaH. And then you try to compare the melt pool profiles, the melt pool depth, the melt pool width, so that you can extrapolate or you can predict the process or the process dynamics for the multi-track nature. So the very important part of the process modeling or the simulation is this first point, which is calibration. Why we need calibration? Because we have to imitate, we have to replicate the actual scenarios, actual fractional coefficients, actual absorption coefficients. These are only obtained once calibrated successfully, and then we can go for the multi-track simulation. Again, we have started with certain study of multi-track, which is an experimental study, and we experimental plus modeling study, and we try to model or we try to simulate that actual process with AM PravaH. So in this multi-track or in the single track, the only difference or only additional parameter is going to be hatch spacing. Those who know, the hatch spacing is nothing but the space between these two adjacent tracks. That means the first track, the second track, the third track, the fourth track. So laser power is already there, scan speed is already there, layer thickness is already there. The additional parameter here is hatch spacing, which is going to play a very important role in producing the thermal history, the microstructure, and the final property of the part. So whenever we try to think that this part is failed, है ना, हमने एक part इस process से बनाया, एक multi layered part बनाया और उसमें delaminination हो गया, substrate से part उठ गया, और you can say कि वहाँ पे lack of fusion, आपने जब उसकी microstructure पे study किया तो you have seen some pores in the structure, and you go back to the process itself. That is one way. Another way is you try to model that process layer by layer in some modeling tool like AM PravaH. So you can actually predict where the lack of fusion can happen, why the microstructure is going to be like that, why the grain size is going to be like that. These all parameters, these all dynamics you can ascertain, you can model, you can simulate with the modeling tools. These are the results which I am going to show for the study. So we have taken certain process parameters from the existing studies. We try to simulate, we try to imitate that process in our modeling environment. We take the same material properties, we take the process parameters starting from laser power, scan speed, layer thickness, hatch spacing, and so on. We have spot diameter, we have density of the powder particle, we have convection coefficients as well. And then we try to obtain the thermal history, how the thermal history is going to happen. So as you can see, there is 4 tracks. The track is track 1, track 2, track 3, track 4. And we can, in the simulation module, we can decide the actual location where we want the thermal history. Why we want thermal history at that particular point? Because the study shows that there are some abrupt changes in temperature profiles. If the temperature profiles have some abrupt changes, that can be translated into the changes in microstructure, that can be translated into certain defects, some hot spots at these points. So the idea of thermal history modeling or the melt pool modeling is to capture that phenomena, why the temperature is changing at that particular point, and you can simulate it at the very micro scale level at certain point. For example, if it is a 100 micron track, you can actually predict the probe location by setting it at certain length, and you can predict the temperature of it. Again, the validation with the study which you are referring is very important. You have to calibrate it, you have to validate that study, that how the temperature domains are near the actual values. The next modeling observation, apart from melt pool and thermal history, is flow convection. Within the melt pool, the metal is literally flowing. है ना? Metal वहाँ पे flow कर रहा है. जब laser आगे जा रही है, metal flow कर रहा है. When this metal is flowing, the convection currents, the convection currents are changing their behavior, their trajectory, and you can, you can meticulously predict these flow convections with the help of simulation softwares, and you can predict the flow velocities as well as temperatures at that point. So at any particular point, you can certainly predict melt pool dimensions, you can predict thermal history, you can predict flow convections or velocity at that very point. And that will give you a complete picture of process dynamics at that point. So findings of these studies with the actual values, you can this study is recently showcased at one conference, and you can once it is published or accepted for the publication, you can see the actual values that I have taken for the consideration. Apart from that, you have to we have some concluding remarks regarding the three-dimensional multi-physics modeling that can capture heat transfer, phase changes, melt pool convections in LPBF of Inconel 718. We can definitely see the multi-track effect in the temperature profiles. When we are, when we are fusing the adjacent layer in multi-track, the heat accumulation has happened. You can see the heat accumulation has happened, and you can see a definitive spike in the temperature range, which can only be predicted in a multi-track study. In single track, you cannot, ascertain whether it is a temperature spike or not. But when you simulate the multi-track modeling, you can, have a certainty around that heat accumulation. You can predict the exhibiting nature of thermal gradients, which will definitely, direct the microstructure to follow. You can have internal circulation or surface flows, and you can decide a definitive framework to predict the multi-track, multi-layer nature of the LPB. Apart from this niche study on multi-track nature, with the under the guidance of Professor Mukul Shukla, we have published few studies that are dedicatedly on the modeling part of the additive manufacturing. Whether it is of the first study is focused on the melt pool, the second study is focused on the microstructure modeling, the third study is a combination of finite element modeling of melt pool, and using that data to use deep learning and machine learning in additive manufacturing. So you can go through these studies if anyone interested in the domain of modeling, and you can see how these modeling tools like AM PravaH can be beneficial, or can be foundational stone for your study, for your research, and for your work. And these two on the bottom are some studies that I have presented during my PhD tenure at VIT and NIT Warangal. These two are also focused on the thermal history and keyhole porosity. The last studies focused on how keyhole porosity is evolved, कैसे वो बनेगा, keyhole कैसे बनेगा, और keyhole बनते हुए वो porosity में कैसे convert होगा. As you can you have to appreciate that these porosity is detrimental for any produced part, whether you are going to use it in aerospace or defense or drone or whatever the field you are using. The porosity you cannot afford. So this study systematically tells you how to model that keyholing phenomena or keyholing porosity in the LPBF. So I'm just trying to build a picture that modeling and simulation tools are essential to understand the underlying physics. You can have a machine, you can buy the powder, you can print the part, you can test it in a destructive or non-destructive manner, and then you can go back कि क्या गलत हुआ. दूसरा रास्ता ये है कि you have to simulate, you have to model the process first, you have to understand the underlying physics, how it is happening, why it is happening, and then you can have a certain control over the parameter. Otherwise it is going to be a black box approach. You put some process parameters, you select some power, and you print the part, and then you can go on for the actual experimental work. Besides saying this, the experimental validation of modeling work is very important, and that is a fidelity. The fidelity part of the simulation has to be certain with experimental studies or existing studies. That has to be definite. And I want to acknowledge the Paanduv applications for providing the AM PravaH tool to us, and we have utilized it for multiple studies. One I have shown you today, and the CEO Advait sir and Rimjim ma'am for their constant support. Whether whenever we stuck at any point, or they have to they have already arranged some support in the technical field. And I have to acknowledge my college, NIT Allahabad and EKGC Ghaziabad, where I'm sitting right now. And we are at MNIT as well as at AKGC, we are working in additive manufacturing field, whether it is physical printing or simulation or modeling or applications of machine learning and deep learning in additive manufacturing. And these are few references of these studies. Thank you, and I encourage you to utilize that free module or free module of additive manufacturing that Rimjim ma'am had told, and utilize it for the your benefit as per your convenience. Thank you.
We sincerely thank both of our speakers for joining us today and sharing their valuable research insights with the community. Thank you so much, both of you. Our team has developed a comprehensive course on practical additive manufacturing, learning through exercises and numerical simulations. So those who have joined on YouTube, please check out your chat box. There will be a link to a form that you can fill, and you will get the access. You guys can see it like it's available there. Sir, there are a few questions from the audience. Yes. I'll read them out for you.
All right.
The first question is what is that? So the first question is, which software is used for topology optimization?
Yeah, I did mention. You see, you could use, for example, Abacus. You could do ANSYS. You could do in this the popular one, which is cloud-based Fusion 360. All right, but then there's this N topology, which is there for topology optimization. There are plenty of them for generative designs, lattice designs. You name a CAD software nowadays, you have the libraries or modules available.
Okay, sure, sir. And a second question is, what are the physics in additive manufacturing?
Yeah, plenty of physics. Anuj has mentioned. For example, let's say we take heat transfer. Would you like to take, Anuj?
Sorry, sir, I missed the question.
Yeah, which are the physics involved? So, right
So
from
the
powder.
in the multiphysics domain, starting from powder laser interaction, starting from metal evaporation, the solid liquid interface, the surface tension, the heat conduction, convection, radiation transfer to each and every body around it, whether it is powder, whether it is solid substrate. Infinite physics. You can, the challenge is how much you can model, how can you can accurately incorporate in your multiphysics model. That is the challenge.
Solidification. When you said evaporation, then it's like change of phase again back to solid. Yeah.
Sure,
So
sir.
both the solid as well as the liquid physics is all there.
Okay, so the third question is, how does non-spherical particles affect the shape of the melt pool?
Oh, okay. You see, basically, it's all about the laser interacting. See, it interacts on a particular zone. Now, if you have a wavy type of a particle, the way it ought to interact, the laser material interaction, then from particle to each layer, it will keep on changing. So it's like making, if I can give an analogy, it's like making a wall of bricks, but those bricks are of different sizes and different shapes. So if you have uniformly sized bricks, you can get a nice consistent quality interlayer, brick to brick, vertical. So that multi-track, the multi-layer is all nicely going to be governed by the powder morphology.
Okay, well explained. Next question is, experimentally, how each of these defects are analyzed, and can simulations replace the extensive analysis?
Yeah, to some extent, definitely. You see, what happens, like we said, these holes, for example, the porosity holes are like embedded inside, which are not likely to be seen externally by naked eye or even by a microscope. So now then you may start doing what is called the different, I did not cover on those experimental side of testing. For example, residual stress. You can't see a residual stress physically, but it is locked in there. So whether it is any melt pool related defects or for example, like the physical distortion, which is measurable and observable. So those are different things. Each can be calibrated and experimentally validated, tested using different approaches.
Sure, sir.
Yeah. Which we want to minimize, and that's why we are doing all this modeling using AM PravaH and the like.
Yes, sir. Which models are used to run DEM simulation, and which forces are considered in DEM simulations?
In DEM, okay. Let Anish reply to it.
Yes, sir.
So in the DEM, the module is inbuilt in the AM PravaH. Apart from that, you can start with the Abacus DEM module, or you can have a dedicated DEM module which is available. The freewares, you can have the DEM. The forces, the first one is the inertia force. The second one is the friction between the powder particles. The third one is the gravity force under which the powder is affected. And you can, in recent studies, they have, utilized the recoater contact surface force also. So you can incorporate that too, where the recoater is, using the layer buildup. So these are the basic forces.
How does flow convection affects the microstructure and properties of the part?
Okay, pretty standard. Yeah, take it, Anuj.
Yeah, sorry.
How does flow convection affects the microstructure and properties of the part?
Yeah. The flow convection is the last one to the party. Initial studies, they only limited to the melt pool and the the thermal history. But the flow convection pattern is really important, as the density difference, the surface tension forces derived the flow of the melt pool, and these derivations of the flow can have a different equiaxed or columnar structure in the mesostructure of the whole microstructure. When I talk about the mesostructure, in the whole microstructure, there are small patterns of mesostructure which are governed by these thermal histories and flow convections. So flow convections are a part of it, are very important to the microstructure, and they will, they will attain a different microstructure because of the different cooling rates and different, governing physics behind the microstructure.
Okay, sir.
In a layman language, if I can add to it, in basic fluid mechanics, you have a concept called the laminar flow and the turbulent flow.
Sure,
so herein also, when we try to do it on a fast mode or other higher scan velocities, that is which we dream of, and then things go wrong out there. So it's like a trade-off or a battle ongoing between solidification and melting. So unless that balance is struck, you will have a poor quality part. So and that's all the flow convection game.
Okay.
Yeah.
How much accuracy we obtain while predicting melt pool temperature and residual stresses using AM PravaH?
I
So
think typically
with
5%.
different,
Yeah, okay.
yeah, with different studies, we can, ascertain errors in multiple geometry as low as 1 to 2%, and in the range, it always lies below 10%, and majorly in my studies it is around 2%, 4%, 3%, below 5%. That is, actually very good when you are incorporating all the multiphysics. If you are not, for example, one simple explanation is, अगर आपने शुरू ही पाउडर एक्चुअल पाउडर से नहीं किया है और आपने सॉलिड पे ही शुरू कर दिया है, आपने डीएम यूज ही नहीं किया, तो एरर्स ऑब्वियसली ज्यादा आएंगे. तो वो एरर को हम उतना ही कम कर पाएंगे जितना एक्चुअल फिजिक्स को हम इंकॉर्पोरेट कर रहे हैं और जितना सही से इंकॉर्पोरेट कर रहे हैं. दैट इज दी.
True. So yeah, that is it. These are some questions from the audience. Yeah, I hope you guys have in the initial there were some problems with the voice of the meet, but hopefully things are better now. So those who have joined on YouTube, please check out the link. Let me just share it again if it's not there. So yeah, it's available on the chat box.